Hi, my name is Shahnawaz. In this lecture, we are going to study the ideal quotient of two ideals in a ring. This ideal quotient is sometimes also called the column ideal. So let us first define this ideal quotient. So suppose we are given two ideals, say I and j. So these are two ideals, say in a ring A. Suppose we have got these two ideals. Then the ideal quotient which is sometimes called the column ideal. So then the ideal quotient of I and j, which is denoted by I colon j. So this is actually an ideal. This is an ideal defined as, so this ideal consists those elements in a ring A such that if we look at this product, i.e. the product of A with the elements of J, then this set should be a subset of I. Then we call this the column ideal of Ij. So this is an easy exercise to verify that this is what we call an ideal. So suppose we have two elements, say x and y in I and j. Then to prove their sum is in Ij. Now I and x and y being elements of this column ideal, this column means x times j is contained in I, and y times j is contained in I. Now x times j is contained in I means, so this will imply x times this little j is contained in I for all this little j in j. Similarly, this would imply y times j is contained in I for all j in j. Now xj plus yj, which is equal to x plus y times j, because the distribution law holds in A. So this is equal to this. Now this being an element of I for all sorry, this is not subset, this is just the belongs to notation here. So now xj being an element of I and yj being element of I, so their sum is going to be an element of I. So this belongs to I for all this j in I, or this x plus y times j is contained in I, because this is true for all j in j. Now this means that x plus y is contained in I colon j by definition of I colon j, because I colon j contain all those elements in A such that this containment is valid. This is true. So this implies this I colon j is closed under this operation, addition operation. Now to prove it is closed under multiplication, so let A is in A be any element and x be an element of I colon j. Now we have to prove this I colon j is closed under the multiplication by elements of A. So this would imply, now x being an element of A, so this would imply x times j is contained in I, or x times this little j is in I for all this little j in j. Now this again will imply, now I being an ideal and xj being an element of M, so A times xj is also element of I, because I is closed under the scalar multiplication. So this is an element of I for all j in j. So this will imply that A x j is contained in j, because this expression here, this is true for all little j in j. So we can replace this little j by this capital J, and this belongs to notation by this containment notation, not j, I mean I. So or Ax is contained in I colon j, that means I colon j is an ideal. So let us make this an exercise. So I colon j is an ideal of A. So the proof is already done here. Now let us suppose this is the notation. We are going to fix a notation. So if j is some ideal, say the principal ideal, so let j be a principal ideal so let I and j be principal ideals, then suppose I is, now I and j being principal, so I and j they are generated by single elements. So if I and j be principal ideals such that I is generated by x and j is generated by y, then in place of I colon j, we write x colon y. So we don't write these braces here, we don't write like this, x colon y. So this, in place of this, we simply write x colon y. Now if we, this is the notation of first, this is second. So in particular so if suppose this j is the principal ideal, the zero ideal here, which is generated by 0, or let us suppose I is the principal ideal which is generated by 0. So in particular 0 colon j is the set of all those elements in A, such that A when we multiply the elements of j by A, we get 0 here. This is subset of this 0 ideal. Now being a subset of 0 ideal, we simply write this 0 set here. So this is actually the definition of what we call the annihilator. So this is actually the annihilator of this ideal j. So is called the annihilator of j in A, and is denoted by a n of j. So this is the definition of annihilator. So let us make an observation here. So this is the observation. So let D be the set of all zero divisors in a ring A, suppose. Then annihilator of X, if we look at this set here, so it is the set of all elements in A such that AX is 0, or it is the set of all elements in A such that AX is contained in the 0 ideal, or it is the set of all elements in A such that this A is the annihilator of the ideal generated by 0. So it is actually 0 colon the ideal generated by X. So this notation here, so this is actually the set of all zero divisors of X. So that means the set of all zero divisors in the ring A is actually the union of all annihilators, I mean the annihilators of non-zero elements. So X is non-zero. If X is 0, then this annihilator will be annihilator of 0 is whole ring A. So then that means this D is A itself. So this is the actually, so this set D of all zero divisors in A is actually the union of annihilators of all non-zero elements. Now we have this exercise here. So before that, let us do one thing. So let A be over ring of integers and M be M and N. Now Z being a principal ideal domain, so any ideal in Z is actually the principal ideal. So and M and N be two ideals in Z. Then M colon J is actually the set of all elements in A such that Nx is contained in the ideal M. So that means now this Nx will be the element of this ideal M if and only if this M divides Nx, because 4 is in the ideal generated by 2 because 2 divides 4. Similarly 6 is in the ideal of 2 because 2 divides 6. 7 is not in the ideal of 2 because 2 does not divide 7. So Nx being an element of M implies M divides the element Nx. Now M divides Nx implies Nx is congruent to 0 mod M. So this is the linear equation here. So the solution of this equation, the smallest integral solution of this equation is when this x is actually M divided by GCD of Mn. So this is actually the solution of this equation, because if we write here M divided by GCD of Mn, so M certainly divides this number here. So this means then, so this being an ideal of Z means this is also a principal ideal, so it is generated by some element. Now the smallest element, which is the smallest positive integer which is in this set, which is in this ideal, will be the generator of this column ideal here. Now by this congruence, uh, we note that this is the smallest positive integer which is in this set, which is an ideal. So this column is actually, so this implies, so then m colon j is actually the ideal generated by this number here, m mod mn. So that means if we look at the, so if I is over ideal generated by suppose 6 and j is ideal generated by suppose so if this is so suppose it is generated by 12, so this is generated by 12 and j is the ideal generated by 18. That means this I is actually the set of all multiples of 12, and this the ideal generated by 18 is actually the set of all multiples of 18, integral multiples. So the column 12 column 18 is all elements x such that x times 18 is 12. So this is actually the ideal generated by 12 over GCD of 12 and 18. So this is GCD here, so which is actually 12 divided by GCD of 12 and 18 is 6. So this is actually the ideal generated by 2. Now let us do some exercises on the quotient ideal. So first exercise is that I colon j always contain the ideal I. So this ideal is bigger than the ideal I itself. So let us first write here, let I, j and k be ideals in a ring, say A. Then so this is the first item. The second item is that I colon j times j is contained in I. Note that this is the product of these two ideals, hence this is again an ideal. The third is I colon j colon k is actually equal to I colon jk. Then fourth is if I take intersection of ideals I sub I and take it as column with ideal j, this is actually intersection of I sub I colon j. And finally, if I look at this ideal I colon sum of ideals j I where sum runs over I, so this is actually intersection of all these column ideals I colon j I. So they are all trivial exercises. So first item is we have to prove, so to prove I colon j contains I. So note that, so let so what we have to prove, this is here. So for all, so this is solution first, for all say x in I, we have x times a is contained in I. Since I is ideal, so I is closed under scalar multiplication. So if we take any element of a and any element of I, their product will be in I. So this is true for a as well, because if we take any element in a and any element in I, then r times x is in I. So this is true for all r in a. Now if this is the case, that means a times x, which is equal to x times a, is contained in I. So that is what we write here. So this is true. So the reason being, since I is an ideal, this is the reason of this containment. Now in particular, this is also true if we write in place a the element of j. So in particular, x times j is contained in I, because this containment is true for a, hence it is true for any subset of a. In this case, j is its subset, so this is true for I as well. So that is, by definition, this means x is in the ideal I column j. So this proves item first. Now second, let us look at the solution of second. So we have to prove I column j product with j is contained in I. So let x be an element of I column j. So this implies xj is contained in so xj is contained in I. So this is true, which is true for any x in I column j. Now if this is true for any x in I column j, so in place of this x, we can replace this set, we can write this set I column j here. So hence I column j times j is contained in x. This proves the item second. Then we have item third. So now what we have to prove? We have to prove I column j column k is actually I column jk. So we are going to show first this containment. So let x be any element in I column j column k. So this is any element. Then this means xk is contained in I column j by definition of the quotient ideal, and hence now xk being the subset of j means x and this little k and j is contained in I for all little k in k. That is x, this capital K, j is contained in I. Therefore this x is in the column ideal I column kj, which proves the first containment. Hence I column j column k is contained in I column jk. Now to prove the reverse containment, we have, so let us now suppose this x is an element of I column jk. Then this means x times jk is contained in I, and hence for all y in say k, x, so we can write here, since jk is kj because wording is commutative, so we can write x j and this y here, because y being an element of k, so we write here x j y. In place of this we write x y j, because we are dealing with commutative rings. So this means x y j is contained in I for all y in k. So this is not necessary to write again. So this means, so therefore this x y is in I colon j for all y in k. Now this is true for all y in k, so in place of y we can replace this y here. This means x times k is contained in I colon j, or equivalently x is in I colon j colon k, which proves the reverse containment, and hence I colon j k is contained in I colon j colon k. So this proves the third item, sorry. So finally we have the fourth item. So note that x belongs to the so we have to prove intersection of these I sub I colon j is actually intersection of I sub I colon j. This is what we have to prove, where this intersection runs over I. So x will be an element of this set here if and only if x j is contained in the intersection of these ideals. So this means, so this is if and only if xj is contained in I sub I for all I. So this is if and only if x is in I sub I colon j for all I, which means that x is in the intersection of, because this is true for all I, so this is in the intersection as well. So this proves item third. Hence, so this is if and only if condition, though this implies this and this implies this, so hence intersection of these ideals column with j is actually intersection of these column ideals. So finally we have the fifth item. So now let us suppose, so here we have to prove I colon with sum of ideals ji is actually intersection of I colon, sorry, intersection of I colon these ji's. So let x belongs to I colon sum of these ji's, where sum runs over I. So then now ji being the subset of this sum, now ji being a subset of this sum of ideals, we know that x ji, which is subset of sum of x times sum of these sum ideal here. So x is here, so that means x times this ideal is in I, is contained in I. So this is true for all I. So this is true for all I. That means this xj, this means this xji is contained in I for all I, which further implies x belongs to I colon ji for all I, and hence x belongs to the intersection of I colon ji, where this runs over this intersection runs over I. So this proves one containment. So hence I column with these some ideals, sum of ji's, is actually contained in the intersection of these ideals I column ji. Now to prove reverse containment, let x belongs to the intersection of these ideals I column ji. So this implies x is in the I column ji for all I, or x times ji is contained in I for all I. That is equivalently, if x ji is contained is in so if xji is contained in this I, that means xj1 xj2, so this is true for all I. So then the sum is also in I, so xj1 plus so on plus xjn is also in I. This further implies x times sum of these ji's in I. So equivalently this implies x times this ideal here, this is also contained in I, and hence x is in I column is ji's. Therefore this intersection is actually contained in this column here. So this proves the last item.